Welcome to this explainer. Today we're diving into a really fascinating IEEE research paper that essentially plays digital detective to uncover a massive blind spot in cybersecurity. The paper is called Disparity Analysis Between the Assembly and Byte Malware Samples with Deep Autoencoders. If you've ever thought the industry might just be accidentally ignoring half the fingerprints left at a digital crime scene, well, you are absolutely in the right place. Here is our roadmap for the explainer today. We're going to cover the malware blind spot, compare assembly versus byte files, introduce our AI detective, the Deep Autoencoder, analyze the lab results, deliver a verdict on the disparity, and finally, look at how we use all this to actually build better cyber defenses. Let's get right into it. Section 1. The malware blind spot. Let's look at the escalating threat landscape of IoT malware and the dangerous gap currently plaguing the industry. You know, reports of malware attacks, especially in the Internet of Things, are just skyrocketing right now. But the truly alarming part isn't just the sheer volume, it's how they're evolving. Malware authors are getting incredibly sophisticated, using advanced data compression and obfuscation to completely mask their malicious code. And because of these slick disguises, our current deep neural network detection models are really struggling. We're seeing super high false positive and false negative rates. Essentially, the security alarms are either blaring when there's absolutely no fire, or they're staying completely silent while the house burns down. Which led the researchers to ask a critical question: are we ignoring vital clues in malware? Which brings us to Section 2, Assembly versus Byte Files. The researchers noticed a really distinct pattern in how the industry was actually interrogating these malicious files. So when you look at standard malware datasets, like the famous Microsoft malware dataset, they usually contain more than one type of file for each sample. You've primarily got byte files, those are your raw binary sequences, and then you have the assembly files, which contain the low-level code instructions. Now, historically, the cybersecurity industry and most machine learning models have relied almost entirely on byte files as the absolute gold standard for analysis. They pretty much completely ignore the assembly codes. The core hypothesis of this research is that assembly files contain fundamentally different, vital features that are just completely missing when analysts only look at the raw byte files. I mean, if they're actually different, ignoring one means we're basically fighting malware with one hand tied behind our backs. Section 3. Enter the Deep Autoencoder. To prove this disparity actually exists, standard classification tools just wouldn't cut it. They needed a specialized forensic tool to act as a digital sketch artist. And that brings us to the Deep Autoencoder. So what is it? Well, an autoencoder is an unsupervised neural network that basically teaches itself to reconstruct whatever input data you feed it. It compresses the data down to its absolute core features and then tries to rebuild it from scratch. Think of it like a highly specialized translator. If it perfectly learns the language of file A, it can easily translate and reconstruct file A, right? But if you hand it file B and it totally fails to translate it, giving you a super high error rate, well, that proves file A and file B have completely different underlying features. That failure effectively flags file B as an anomaly. The actual engine powering this digital detective is a convolutional neural network, or CNN, and it contains exactly 187,009 trainable parameters. The structure here is incredibly clear. It starts with the input, moves right into an encoder with two convolutional layers to compress that data, hits the hidden layer where those really deep features are extracted, and then runs through a decoder with upsampling layers to reconstruct the output. It's just a sleek, simple, but highly efficient engine custom designed to extract deep features from that Microsoft malware dataset. The methodology they used is this beautifully elegant anomaly detection loop. Step 1, you train the autoencoder on one file type. Let's say the assembly data. Step 2, you ask the model to reconstruct the other file type, the byte data. And step 3, you measure the reconstruction error loss. It's straightforward. If the error is high, it absolutely confirms the presence of unknown features in that second file. This whole process splits into a very distinct training and testing track, and there's a really critical quality control step right in the middle, the loss threshold. Before any actual testing even happened, the team strictly fine-tuned the model. They ran it through epochs until the training loss dropped below a 0.5 threshold. They had to ensure the model was highly accurate on its training data before they ever tried throwing a curveball at it. Moving on to Section 4, Analyzing the Lab Results. Now we actually get to dive into the data and see exactly what happens when our digital detective interrogates these files. Okay, let's look closely at these results. In one scenario, the model was trained strictly on assembly data. Its error rate when reconstructing assembly data is very low, hovering right around 0.05. But when it's suddenly asked to reconstruct byte data, that error massively spikes to around 0.18. Then we see the exact reverse.
The model is trained on byte data, and it reconstructs byte data perfectly. But when handed assembly data, the error violently spikes again. This is literally the smoking gun. Whether it's trained on assembly or byte data, the model sees a massive spike in error when tested on the opposite file type. It fundamentally proves that byte files and assembly files are distinct. They just contain completely different features.
Section 5. The verdict on disparity. But, science requires rigorous skepticism. The researchers knew critics might look at those spikes and argue it was just random background noise.
Skeptics might say maybe the files aren't fundamentally different. Maybe one just has more noise and it's confusing the model. So to completely silence those critics, the team ran a second, pretty ingenious experiment. They intentionally polluted their own data. By deliberately adding a 0.3 noise factor to both the assembly and byte data, they leveled the playing field. Then, instead of a standard autoencoder, they deployed a denoising autoencoder. Now, a denoising autoencoder's entire job is to take noisy, messy data, clean it up, and reconstruct the pristine original. They wanted to test, if we train it to clean noisy assembly data, can it also clean noisy byte data?
Once that noise is introduced, the results are just undeniable. The denoising autoencoder trained on noisy assembly data is perfectly capable of producing clean assembly data, but when it's asked to reconstruct clean byte data from noisy byte data, the loss jumps from around 0.08 all the way up to 0.5. And the exact same failure happens in reverse. Even after completely ruling out random noise as an excuse, the model still failed spectacularly to reconstruct the opposite file type. This definitively proves the feature disparity is real, guys. It is not noise, it's fundamentally unique data.
Which brings us to our final section, Section 6, Building Better Cyber Defenses. Because the really crucial point here is, what does this actually mean for the real world? How does proving this data disparity help us fight malware? Well, the paper's conclusion provides a very clear and urgent directive. To quote it directly, researchers should use both the assembly and byte files throughout experiments for better malware detection and classification. This is a stark warning, honestly. Continuing to rely solely on byte sequence data is leaving our security systems incredibly vulnerable to advanced obfuscation. We are literally leaving vital clues right there on the table.
Let's break down the tangible benefits of adopting this dual-file methodology. For organizations, it means building incredibly robust threat detection systems. By analyzing both byte and assembly files, you're eliminating a massive blind spot, which makes it infinitely harder for malware to sneak past your firewalls disguised as benign code. For students and researchers, this unlocks thrilling new vectors for machine learning. It challenges the academic community to design novel hybrid architectures capable of processing multimodal malware data simultaneously. And for cybersecurity communities at large, the biggest win is drastically lowering those frustrating false positive rates. When an alarm sounds, it will actually mean something.
We've seen how deep autoencoders can act as brilliant digital detectives, proving once and for all that assembly files hold secrets we desperately need to defend our networks. So, as you consider how to apply these dual-file methodologies to your own systems, let this final question challenge you. If AI can uncover vital clues we've been completely ignoring in malware today, what other hidden details are we missing in the fight against cyber threats? Thank you so much for joining me for this explainer. Keep asking the hard questions, and I will see you next time.